Welcome. In this video, we explore how transformer networks analyze complex physics data. We will see how the attention mechanism allows a neural network to discover correlations inside measurements, visualize what the network focuses on, and finally combine information from different detectors. The figure shows a measurement of radioactive decays resulting in a charge measurement Q as a function of time t. Our scientific task is to count beta decays while rejecting alpha and gamma signals. The figure also introduces the central computation of a transformer. The output matrix Z is calculated from three matrices called Q, K, and V, meaning query, key, and value. First, Q multiplies the transpose of K. The result is scaled by the square root of D prime, the dimension of the latent feature space. The softmax function converts the scores into normalized weights, which are then applied to V. In simple terms, the transformer compares queries with keys and uses the resulting weights to combine the value vectors into the output matrix Z. This entire computation forms the so-called transformer head. This figure shows the typical physics use of the transformer as an encoder. The measurement sequence enters at the top. The transformer analyzes correlations between time bins and produces an enriched representation. A fully connected neural network then uses this representation to classify the event, for example, identifying beta decay signals. Transformers usually use multiple heads running in parallel. Each head has independent weight matrices and therefore learns different correlations or features in the data. For example, one head might detect features typical for beta decays, while another captures background patterns. The outputs of all heads are concatenated and projected with the weight matrix W prime. This step combines the knowledge learned by the different heads into a single representation that can be used for classification, regression, or further neural network layers. Let's have a look at the columns of the attention matrix again. By summing the columns of the attention matrix and normalizing, we obtain the vector A. This vector highlights which time bins receive the largest overall attention and therefore contribute most strongly to the model's decision. Let us now look at a physics application. This figure shows a simulated sky map of cosmic particles arriving on Earth. Star symbols mark galaxies of type S. Particles from those galaxies are color-coded by their energy, while other particles appear in light gray. A transformer network is trained to identify the particles originating from these galaxies. Here we see attention maps from 3 of the 8 transformer heads. Colored regions indicate directions where the network assigns high attention values. These regions correspond to directions from which particles from the target galaxies typically arrive. The visualization shows that different transformer heads specialize on different sky regions and share the analysis task. Self-attention alone does not know the order of the input data. The permutation operator P rearranges the entries of the input vector X. If the input data are permuted, the query matrix Q is permuted as well, and the same happens for the key and value matrices. As a result, the attention output is permuted in exactly the same way. This property is called permutation equivariance, meaning the transformer needs explicit positional information. To include positional information, we add a positional encoding matrix H to the input matrix X. Both matrices have identical dimensions, producing the combined matrix X prime. A common positional encoding uses sine and cosine functions. The index I represents the position of an input element, while delta runs over the components of the encoding vector with maximum dimension d prime. These periodic functions generate unique vectors describing the positions in the sequence. This example shows positional encoding learned from a hexagonal sensor array. Each sensor produces a feature vector xi and receives a trainable positional encoding vector hi before entering the transformer. The similarity between encoding vectors is measured by the scalar product between the red-marked sensor Y and all other sensors J, resulting in the cosine of the angles between them. The yellow color reveals that sensors in the same hexagonal ring obtain similar encodings. The transformer has therefore learned the geometric symmetry of the detector directly from the training data. Before entering the transformer block, input data are embedded and combined with positional encodings. In addition, a class token CLS is input as a placeholder to convey the results of the subsequent transformer block. Inside the block, the data pass through normalization, multi-head self-attention, and a feed-forward neural network. Residual shortcut connections help stabilize training, and multiple transformer blocks can be stacked sequentially. A variant of transformer networks is the vision transformer that applies the attention mechanism to two-dimensional sensor arrays or images. The image is first divided into smaller patches. Each patch is flattened into a vector, mapped into latent space by a neural network and combined with positional encodings before entering the transformer. This allows the network to analyze spatial relationships between different image regions. Finally, we consider cross-attention. The figure shows a particle first leaving signals in a tracking detector and then producing a shower in a calorimeter. Cross-attention combines information from both detectors. The query matrix Q comes from calorimeter data X, while key and value matrices originate from tracker data Y. The resulting attention matrix connects measurements from both detectors and produces the output matrix Z. Transformers analyze measurement data by comparing query and key representations and combining information through attention weights. Positional encoding enables the network to understand spatial or temporal order, while multi-head attention allows different parts of the model to focus on different patterns. Together, these ideas allow transformers to extract physically meaningful structures from complex experimental data. Thanks for watching, and enjoy discovering what your data is trying to tell you.